Hey, Travis. That was good. Chemistry humor. Okay, I'm going to go ahead and get started because this is kind of a long lecture. Does anybody remember what we talked about in the online videos this week for this class? This is machine design. We talked about what? Lecture number 1 was on principal stresses. Lecture number 2? Failure conditions. Good call. It's always nice when people pay attention. Now, when you're calculating principal stresses, I gave you all of the stresses, the x, y, z, x, tau xy, tau yz, tau zx values. You may have to calculate those yourself, or use solvers. But the ultimate goal is, can you figure out what the principal stresses are based on loading conditions? So heck yes, that's what we're doing today. Oh, I was going to grab my book too. Did not do that. You have your book? I'm going to grab my book anyways, but thank you. I'll be right back. Okay, sorry about that.
We're on camera, we got you. We got him. Boom. Look at
I'm gonna have to watch a YouTube video now. Just to figure out which one of you hooligans did it. Unless one of you cleverly hid the camera while the other one did. Scandal. Scandal. Okay, so this is what we're talking about today. We're going to do an example that covers everything. So, let's say, oops, nope. What we're going to say is we are analyzing a vehicle axle. Okay? So this is going to be our axle. We're going to have wheels supporting both sides. We're going to call those simple supports. So they only provide vertical force on this axle. This axle is not moving, so there's not going to be any torsional moment or anything. Oh, I even thought about it. No, I won't. We're going to have 2 bearing loads located a third of the way down the shaft. So this is L divided by 3, L divided by 3, L divided by 3. These 2 forces are going to be equal. We got our R1y, and we got an R2y. We're going to go ahead and say that F is equal to 1,800 pounds. And we're going to go ahead and say L is equal to 18 inches. Okay? So this is your free body diagram. Convenient. I'm going to go ahead and give you the cross section. The cross section is, for this, the outer diameter is equal to 2 inches. The inner diameter is going to be equal to 1.5 inches. So it's got a 1/4 inch metal thickness. We'll go ahead and say that the yield strength for this is a ductile material. What's the difference between ductile and brittle materials?
Plastic deformation.
Plastic deformation in which material?
Brick or brittle is not. And then ductile, there is plastic deformation.
Yes. In ductile materials, you will have a plastic deformation. Okay, if your axle bends, you've got problems. Okay, if it breaks, you have problems too. But since this is a metal structure that is ductile, if it even bends, it's not going to function properly. So bending, or here what we're going to call yielding, is a failure criterion for this. We do not want our axle to bend. Whoa. And we're going to say that our yield strength is 30 kpsi. Okay? So fun times with an axle that's only this long. All right, so we've laid out the problem. Now the first thing that we have to do is, well, that I would suggest doing is, okay, we got the free body diagram, we got our forces. Let's go ahead and solve the free body diagram. And we'll come up with our shear force and bending moment diagrams. Okay? Now the reason why I bought my book is because somebody has already done that for us. So, yep. Table A9, section 9. A9, table 9. This says that R1y is equal to R2y, which is equal to F, which is equal to 1,800 pounds. Okay? This also gives me diagrams for V and M. For the shear force, it looks like this. Oh, nope. Where this is located at L over 3. This is located at 2L over 3. Okay? The bending moment diagram looks like this. Zoop, 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 zoop. Okay? We're here, the equation. The moment equation is mzz is equal to F times X. Here, the moment equation is mzz is equal to F times L over 3. And here the moment equation is mzz is equal to F times L minus X. Okay? The shear force equation. This is equal to F, and this is equal to negative F. Okay, so thank goodness for tables in the book that give us answers. That's going to solve us a lot of math. Okay. Because I saved time, that allowed me to dance in class. So let's do math. We already know what F is. This is 1,800 pounds. This is negative 1,800 pounds. Sweet. This maximum moment value is equal to FL over 3. So that's 1,800 times 6, which is equal to 10,800 pound inches. Okay. So, step 1. Free body diagram, done. Step 2. Loading graphs, done. Now, this is in the X direction for both of these. If we were loading this in also the Y or Z direction, we would have to draw those loading graphs in the Y and Z direction. No, don't do that for this one because there are no loads. The loading graphs in those directions. This is right here. Let's see, this is the YZ plane. There's no loads in the Z direction. There are loads in the Y direction, but that doesn't change in the Y direction. So it only changes in the X direction. So we drew our loading graphs in the X direction. Didn't need to in the Y or Z directions. Great. What's the next step? We haven't discussed this. Find the critical stresses. Locations. Okay? What do I mean by critical stress locations? This is where on this shaft are the greatest stresses probably going to occur. Okay? Critical stresses are likely to occur at really small geometries. So if your area shrinks for some reason, that's what's going to happen. Okay? Anytime you have a change in geometry, such as a curve or a hole or a slot, you're likely to see a critical stress. Okay? So those are just geometric properties that could determine where a critical stress could occur. Okay? Now we're also talking about point of application of forces. Just simply applying a force could cause a member to fail. All right, and the last critical stress location, maximum loading locations. Do we have any geometric changes in our axle that we're analyzing? We don't have anything. We don't even have a single hole. Okay? This is a solid, continuous cylinder. We don't have any changes in geometry, and we don't have any small geometries. Okay? If the what?
It does kind of have a hole in it.
Yeah. It's a cylinder. It's not a hole. It's a. Fine, it's a hole. That's not the hole I'm kind of talking about. It's not even like a hole this way. Now you derailed my whole lecture. Oh, yes. Writing your mom on the board did not derail my lecture. I'm used to that. I'm also used to like getting a swirly in the middle of class, but that's a different story. Yeah, wouldn't have deterred me. Okay, what am I doing now? Right, okay, so critical stress locations. We don't have any changes in geometry. So our geometric conditions aren't really going to apply here. in a different one where we had a stepped shaft or different sizes of shaft all connected together, then those would pose places where we would need to analyze the critical stresses. But we don't need to on this one because we don't have those. We do have loads, which are kind of important for failure. So one of these two are going to identify where our critical locations are. Or actually both of those should identify where your critical locations are. We have forces applied at 4 locations. Here, 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 and here. Okay? Automatically you should be looking at those spots. Okay? We plotted these diagrams. We have maximum values here, here, and here. Which ironically, this is not a maximum value, while this is. And this is not a maximum value, while both this is. So they kind of peak at different spots. Okay? So that's interesting. We're looking at these 4 locations also. These are critical spots to look at. So we're looking directly at the lines. Well, I can say right here, this moment value is basically its maximum. And same right here. It's basically at the maximum. And at that location, this shear force also is at a maximum. So, not only are those 4 critical locations defined by loading, not only are they important for determining critical stress locations, but it turns out that's where the maximum loading occurs also. It is not uncommon for those to be the same thing. Okay? So, now do we need to go analyze these spots right here? I can promise you these 2 spots over here are not going to be anywhere near as critical as these because the moment is not as large. So, 2 spots on this axle we need to analyze. Okay? We know where they are. Excellent. Number 1. Critical stress location at L over 3, and I'm going to say minus because it is just a hair to the left of that when we still have a shear load. Okay? And then I'm going to write number 2. I'm going to give some space here because I'm going to fill this out with other stuff. At 2 L over 3 plus signifies it's just a hair to the right. Those are the 2 critical locations that we're going to have to analyze. Okay? What is the shear force in the y direction? Well, we're going to go ahead and write out what all of our loads are at the critical stress location. Okay? So the next step is, now that we've identified these, identify loads in geometry at critical stress locations. I think I have 2 more points to make down here too, so hopefully you have space in your notes or you can add those in later or something. Okay, so we're going to identify loads in geometry at both of these locations. What kind of loads do we have present in our system? Well, there's only 4 kind of loads you can have. What are they? Bending, that's 1. What? What did you say?
Torsion.
Torsion, okay. Bending, torsion. That's not what you said at first.
It definitely is.
Okay, so bending and torsion, what else? What are the other 2?
Shear.
Shear, which we drew that up here. And the last one is
Axial.
axial or normal forces. Okay, axial normal forces create a sigma. Sigma causes an extension or a compression. right? Anytime you have a sigma, it'll cause it to extend or contract. Shear force causes a shear stress. Shear stress causes a distortion. It is not an extension or compression. It is an actual distortion. Okay? Bending stresses create normal stresses, your sigmas. Because again, at the top of the beam, where there's tension, it'll be stretched out. At the bottom of the beam, where it's in compression, it'll be flattened. It'll smashed. Okay? So, and then lastly, torsion creates shear because it doesn't cause it to get bigger. You don't twist it and it grows, at least for most materials. Some materials, that's not true. But not the materials we're looking at. But you twist it, it doesn't grow, it just deforms. Okay? So that's what we're dealing with. Just keep that in mind for later. I need to give you all an equation sheet. I will have to work on that sometime this weekend. Because that should summarize everything we've learned so far when it comes to static failure, which this is called static failure because we're not changing loads at all. All right, so at this location, which one of those 4 loads are present? Which of those 4 loads are present?
Shear.
We got shear. We have a VY. What else?
Normal. Brendan.
Do we have any normal forces here? Normal forces have to have axes aligned. So there's no normal forces. There is a shear. What other kind of loading do we have at our critical location? We have bending. Do we have any torsion? But we know we have these two. And we're going to say we have these two at both locations. Okay? So that's fun. All right, 2 types of loading. Let's go ahead and just write down what they are. We know that Vy at L over 3 minus is this location right here. That force is equal to 1,800 pounds. We know MZZ at the location right before, we're going to call it 10,800 pounds. Pound inches. Okay, at this location here, Vy is equal to negative 1,800 pounds. And MZZ is equal to 10,800 pound inches. Okay, so we've identified the loads. We don't have any other loads at this location, which means this is going to create a stress. This is going to create a stress. But those are the only 2 loading conditions that are going to create a stress at L over 3. We don't have any axial, any torsion. We don't have anything else. We don't have any shear forces in any other directions. We don't have any bending moments in any other directions. We've listed every single loading condition that occurs at L over 3. Right? So now that we have that, we also need to state geometries at those critical load locations. Now our geometry doesn't change. It's the same here, 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 and here, so that does make the problem a little nicer. But I am going to explicitly write that out now at the critical load location, because you need to know what the geometries are at that location. Okay? So, shear force, the formula requires an area. We need to know what A is. How do you calculate the area for this cross section? What is the area? What area are we talking about? This thing? Why did you say that? Why aren't we doing the area of this? This is what's actually carrying the load. You're right. I'm just giving you a hard time here. This is what's carrying the load. It is the cross-section. The load is being carried inside of the beam, along the beam. So this is what's carrying the load. This is what you care about as far as area and inertial properties. Now that said, if we had a z-directional load here, your area wouldn't be this one anymore because it would be carrying a load in a different direction. But because we're carrying these loads across that cross-section, it has to be this one. By the way, if we had a z-directional loading here, I would tell you to throw it in SolidWorks and don't even worry about it. But you don't. So we're dealing with much simpler loads here. That's why we're talking about this. Our area is going to be the area of this cross-section right here, which that area is given by pi over 4 times outer diameter squared minus inner diameter squared. Okay, which that's equal to pi over 4 times, just making sure I'm still in the frame, 2 squared minus 1.5 squared, which is equal to beep boop boop boop. Zero 0.4488 inches squared. Feel free to check my math because I may be wrong. Also, don't check my math because I'm never wrong. We also need the moment of inertia. As Sean pointed out, our load is being carried across this face, which means we need the moment of inertia of this face. Okay? So the moment of inertia is going to be the bending along the centroid axis, the resistance to bending. If this were a taller shape, it would have a higher moment of inertia. If it were a shorter shape, it would have a lot less moment of inertia. Paper has a big bending moment of inertia in this direction. You actually have to tear it in order to bend it. But you can bend it in this direction really easily. So the direction of the bending moment does change. Well, this is a cylinder, so actually the bending moment of inertia is equal everywhere, in every direction. But ignore that. If this was an I-beam in this configuration has a great amount of bending strength this way. You load the I-beam this way, in bending it, it doesn't bend very far. If you try to bend it in the other direction, loading it this way, where this is now the axis that it bends across, this actually bends a lot. This is a lot easier. You guys want to bend one with your hands? You might be able to do it with a small enough I-beam. You want to try to bend it this way? Oh, heck no. Yeah.
It's wrong.
No, it is. All right, what is it?
Yeah, it is.
You could have kept it up.
It's a can-do attitude that I need to have play as a motivational listening device as I try to fall asleep at night. So if you care to record yourself, please let me know. All right, the I value for this. This is going to be the I value for bending in the Z direction across this axis. I will go to my table in the back of the book because it lists a bunch of I values. And for a hollow circle, bending along that axis, which is IZZ, is equal to, that's just IZ, equal to pi over 64 d to the fourth minus d to the fourth. Okay, which is equal to pi over 64 times 2 to the fourth minus 1.5 to the fourth, which is equal to, let's see if I can do it right this time. It's still wrong. I haven't even given an answer yet. Zero 0.5369 inches to the fourth. Feel free to check my math again, but also you're getting a lower grade on this class. You get a 0 for attendance for this class today. So do all the rest of you, but that doesn't matter. I don't get participation points. But you especially don't get any participation.
Hey, I'm also watching the stream.
You're the other viewer.
We have 2 viewers.
It's terrible. Yeah. So, no, it's an all-time high for my live stream. Sweet, my mom's gonna be so proud. Okay, so now we know what the area and we know what the bending moment is. You can also, if you're dealing with torsion, you'll have to calculate the polar moment of inertia here, J. Not going to do that because we don't need it. We don't have any torsion. The area and the moment of inertia in the z direction are both equal here too. So 1.37 inches squared and 0.5369 inches to the fourth. By the way, I knew I got that area calculation wrong because I had a different number on Tuesday. Exact same problem, different number. However, I did get that moment of inertia, so joke's on you. Okay, now I know my values. I know my geometries. This is an easy transition to our next step. Calculate stresses. And determine direction. Okay, so I'm going to calculate these stresses now. I have found my 2 critical locations. I'm going to erase this because I no longer need this. Also, I have to only work on a small portion of the board or else I have to continuously rotate the camera. And I don't want to do that. It's Friday. So I'm going to calculate stresses. What 2 types of loading do we have here at critical stress location 1? We have shear and bending. So we need the shear formula and the bending stress formula. Okay? I'm going to throw those at you because I have those memorized. So for 1, tau, okay, what direction is the shear loading caused by Vy? What direction is that stress going to be? First of all, is it a tau or a sigma?
Tau.
It's tau. Okay, why is it tau?
Because it is.
Because it's not normal.
Because it's not normal. I'm a tau. No, it's because shear stresses cause deformation, not stretching or compression. Okay?
I was trying to say that.
Yep.
Yeah.
You just made it really easy to relate to a stress, though. So, this is a tau because it's deformation. All shear stresses are taus. All of them. Any stress that's caused by shear force is a tau. Okay? Now there's a caveat on there, but ignore that. There are some normal stresses that are caused by shear stress applications, but they're small enough that we ignore them. Okay. What direction is this shear force, the shear stress, going to be in? I'm going to draw a unit cube. I'm actually going to take a slice of this thing. Dun, 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 dun. Dun, 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 dun. Okay, so we're carrying over this entire face, we are carrying shear force Vy, and we're carrying a bending moment M. Okay? Over this entire face. So what that means is that the sum of all of these shear stresses across this face is going to sum to Vy. In general, if you only look at the front half of the loads. Okay? And it means that the sum of all the forces here that are going to be exerted are going to sum to a bending moment equal to M. Okay? That's what it means when we start taking a cross section. Okay? So what we know is we're carrying little amounts of force in this direction related to Vy. What direction is that? Remember, this is the YZ face. What direction is the load occurring in? It's in the Y direction. What face is that occurring on? It's on the YZ plane, which makes it the X plane. That's the same thing. So, force in Y on X plane means this is tau xy. Okay? Good. So, force in Y on X plane, what that means is if we go in and we look at a square like this, we have tau xy because this is the X plane, this is the Y direction. So this is looking actually in the YZ direction, interestingly enough. This is the X plane, Y direction. Now, counteract that, you have a force here, you have a force here, and you have a force there, because that's what shear stress does. Shear stress, you apply one force, you end up with 4 on your unit cube. These two counteract each other because that's how it transmits through the element. These two exist to counteract the moment that is created by these two being transmitted through the element. Okay? So, these 4 forces, this is in the Y direction on the X face. What face is this on? It is also on the X face because this face shows up I'm wrong here. This face shows up only on the X direction. You're looking down the X direction, you see that face. Okay? So, this here is also tau xy. Okay? What about this one? What face does this stress occur at? It's on the Y. If you're looking down the Y-axis at it, that's how you see the face. It extends out in the X direction and the Z direction. So this occurs on the Y face. In what direction is it acting? It's acting in the X. I had to change to X because I was wrong. It's acting in the X direction. Okay? So this also happens to be tau xy. All of these are. One tau xy creates 3 other tau xy's on the same unit cube. Okay? And those stresses look like this, looking into the material. So that's a 3-dimensional view. Okay, so we have tau xy's now. This is a tau xy. It is the easiest way to figure that out, though, is just by knowing the force is in the Y direction and it has to be carried along the X plane. This is the X plane. And this carrying the force in the Y direction, therefore this is a tau xy. Yes, there are engineers who still struggle with figuring out what shear stresses go where. That's why I'm trying to help you there. Okay. The equation for shear stress is V over A, Vy over Ax times C, where C is a constant that you multiply this by to get the stress. So, I'm going to go ahead and erase this quick. I'm done yelling. You can find C from the book. I'm going to go ahead and flip to that page. It's in chapter 3. Come on, give me the goods. Come on, cash money. Come on, there it is. So from table 3.2. C is equal to 2. So that means tau xy is equal to Vy over Ax times 2, which is equal to, we know what Vy is, 1800. We know what Ax is, 1.37. And we know what C is, which is 2. Calculate that out. Tau xy is equal to 2628 psi. And bing bing. All right. What kind of stress is created by a moment load? Is it a shear stress or a normal stress? It is a normal stress. Because what happens is the top is in tension, the bottom is in compression, or the other way around. And a tension or compression is a normal stress. It squishes or stretches it out. Okay? So this is a sigma. What direction is the normal stress in? If we cut that cross section out, what force is required to maintain tension or compression in this element? What direction does that have to be in? If it's in the y direction, it means it's being exerted this way. That means it is stretching or compressing in that direction. Is that correct? Well, not really, because that's not going to create tension on the top, compression on the bottom. If tension is on the top and compression is on the bottom, what direction are the top and bottom going in? What direction is that line? That's in the x. So yes, while the forces are in the y direction, what we end up with is the tension occurs here, compression occurs here, and the forces have to point towards each other to be axial. Okay? So this is a sigma x that is created by the bending. Sigma x, the equation for that is my over I. Here it's an iz because it's bending across z direction. This is equal to, we know what the bending moment is, 10,800 pound-inches. What is y? It's the distance from the centroid to the point where we're calculating the stress. Okay? The maximum value for y here is going to be the distance from that z centroid to the top of the beam or to the bottom of the beam. The beam is symmetrical, so y is going to be equal to half the diameter, or OD divided by 2 divided by IZ, we calculated as 0.5369. Okay, OD is equal to 2, so that means 10,800 divided by 5369 means our bending stress is 20,115 psi. Do we have any other stresses on this element? Well, we do, but they're small enough we're ignoring them. There is actually shear stress created by bending, and there is also normal stress created by shear force, et cetera, et cetera. But we're only going to calculate one stress per loading condition because we're calculating the most important stress. The other stresses are small enough, they're dwarfed. It is almost as if they don't even matter. So we're ignoring them, okay? One stress per loading condition. We only had 2 loading conditions. We're good. This is all we need. Now what we're going to do is we're going to calculate principal stresses. So my step 6 over here is principal stresses. And order of principal stresses. Okay, is this planar loading? Is this planar or is this general 3-dimensional loading? Why do you say it's plane? It's in the y and the x direction. Both show up.
I was also talking about like that loading, like force.
Oh, this actually doesn't matter.
Okay.
This is what matters. Okay? Do we have any z component here? We do not have a tau xz, we do not have a tau yz, and we do not have a sigma z. Which means we are dealing with planar stress conditions, which means we can use Mohr's equation instead of using that gigantic 3-dimensional equation, which is gross. Okay? So, Mohr's circle equation. What we have now is the equation for Mohr's circle is sigma A, sigma B is equal to sigma x plus sigma y over 2 plus square root of sigma x minus sigma y over 2 squared plus tau xy squared. That's the equation. Sigma y is equal to 0. So this is equal to sigma x is caused by bending, 20,115 over 2 plus the square root of 20,115 over 2 squared plus 2,628 squared. Okay? Sigma A and sigma B come out to be...
Nice sign up.
Thank you. I'm working on my square dancing.
Isn't there like a plus and minus?
It is. This is a plus and minus. Thank you. Squared. So this sigma A equals 20,453 psi. Sigma B is equal to, oh dang. $20,452 psi. Yeah, big change there. Oh wait. Whoops. Hold on. Scratch that. Yep, that was wrong. Negative 337.7 psi. Okay, so what is sigma 1? Sigma 1 is the biggest of all of these numbers. What is the biggest principal stress? We got 3 of these to write down. And I gotta go quick because class is technically over. And at this point, if you need to leave, go ahead, but I need to finish this live stream. So, I won't be upset if you quietly leave the room. What is sigma 1? Which one's the biggest? Sigma A is 20,000. What's the second biggest principal stress? Don't say anything, Orlando. Why did you say 0? It's not up here.
Because we didn't have, it would have been 0 for the, if we did that whole one.
Yes.
equation.
I just felt my heart grow. Love when you guys pay attention to those lectures. It's 0 because, quite frankly, when we stated that this is planar stress, we stated that one of our principal stresses has to be 0. We have no stresses in the 0 direction, so our principal stresses in the z direction are going to be 0. And then this is our sigma 3, which is negative 337.7 psi. Okay? Now, I can honestly tell you that this location is going to have the same 3 principal stresses. I'm not going to go through those calculations. The only difference is that this is a negative sign on your tau, and the only location where tau shows up in this equation is here, and it's squared. So it doesn't matter if there's a negative sign. So you end up with the same 3 principal stresses for both of these locations. Okay? Now, taking the principal stresses, and the goal of this is we want to know what our factor of safety is. We are looking for one number. We have spent all class looking for one number. There's a number of different methods you can use to find that one number. You can use the maximum shear stress theory, MSS. This is a conservative estimate. You can use the distortion energy theorem, which we are going to use. You can also use the other one, the Coulomb-Mohr theory, but that takes into account the compressive stress, and you get the same equation as MSS using that way. If you use it and both the compressive strength and the tension strength are the same. For steel, it has the same compression and tension strength, so we're not going to use that one. There's no reason to. We're going to use this one. This one uses von Mises stress. Von Mises stress, which if you've done SolidWorks analysis, you've seen a von Mises stress before. Basically what it is it is a measure of the amount of energy that is being stored in a single unit element due to the loading conditions. Okay, the calculation for von Mises stress is sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared divided by, I believe it is 2? Nice, thanks. And then you take the square root of it. Okay? And this is equal to von Mises stress, which is a sigma prime. Okay? And then the failure condition, or the safety factor condition, is N is equal to Sy over von Mises stress. So this is what we're looking for. We had to calculate all those friggin' things to find this. I'm going to go ahead and plug this into my calculator real quick. The von Mises stress is 20,453 minus 0 squared plus 20,000, 0 minus 337 plus 337 squared plus 20,453 plus 337 squared 1/2 for 2. This is fun math for your calculator. Von Mises stress sigma prime is equal to 20,623, 624% rounds, PSI. Okay, you want to know what the safety factor is? N, we plug in our SY, which is the strength of the material that we had at the very beginning of the problem. N is equal to 30 divided by 20.624. And N is equal to 1.455. It's a units dimension because it's a PSI divided by a PSI.
KPSI?
Well, I changed them to KPSI. That's why it's a 20 point.
Okay.
Yeah. Okay, any questions on this? Sorry to hold you all late. So I'm going to be posting 3 lectures next week. I'm going to be giving another example over this, because this is gross, but I think you need to know it. We'll talk a little bit more about what failure theory means. Next week we're talking about dynamic loading failure. Next week is gross.
Dynamic.
This is all static.
I know.
This is not, yeah, this is actually fewer steps than what we will be dealing with next week.